Entertainment. I'm your host Dylan Hamilton, guys, and we're back here with the first technical part in the immunity sequence: pathogens and immunity. The reason why I left this last is because it's probably the longest part of immunity, and it can be the hardest bit to get your head around. It's also part of AP1 biology, and let's get straight into it. So, there's a number of different types of responses, but we'll start talking about why a response is needed. So, there's these microorganisms that can cause disease, and these microorganisms are called pathogenic. And these can be grouped into pathogens, which enter the body, and so a subsequent defense mechanism is grouped into two types. First one is non-specific, and these are non-specific to the individual's type of pathogen. And then there's specific immune response, which distinguishes between the individual's pathogens, and a response is tailored to the pathogen involved. So non-specific is like, it doesn't care what it is, it's literally just going to do everything. Specific is like, right, this will only target this disease. So the first form is barriers. So barriers that prevent the entry of pathogens into your body. Your first one is your skin, which is your outer protective covering layer, and this operates as most pathogens can't penetrate unless a cut or wound is present. You also have the enzyme lysozyme, such as in your tears, your sweat, your saliva, and your sweat. It's antibacterial, so you're able to digest the pathogen cell wall. Tears will wash away debris and pathogens from the front of the eye, which is delicate and easily damaged. So tears are quite important. It's good to cry. Epithelial lining covered in mucus is another one. This works by having the respiratory tract containing mucus, which traps pathogens and preventing them penetrating the underlying membranes. You also have hydrochloric acid in your stomach, which kills most pathogens in the food we eat or the liquid we drink. And this is because it gives you a very low pH, denaturing the enzymes of the pathogens. So, phagocytosis then. This is your non-specific, and it's very, very rapid. It's carried out by white blood cells known as phagocytes. Now, capillaries in an area infected will become leaky, and plasma will seep into the surrounding areas. This inflamed part will become swollen with phagocytes and dead pathogens, and the cell debris is called pus. So, your inflamed area will also become red due to the increased blood flow to the area, and a raised temperature will reduce infection by denaturing enzymes in the pathogen. Phagocytosis will include polymorphs and macrophages squeezing through the capillary walls and engulfing the pathogenic bacteria and surrounding the cell debris at the site of infection. So let's just go through the process instead of finish like a little story. So the phagocyte will move towards the pathogen, and the phagocyte membrane will invaginate to enclose the pathogen. Then as the pathogen is engulfed, the invaginated phagocyte membrane will form a vesicle or a phagosome. Phagosome is the key word there. You have to use phagosome. And this will go around the pathogen. Lysosomes will then move towards the phagosome and fuse with it, releasing the hydrolytic enzyme into the phagosome, hydrolyzing the pathogen. Now this soluble digested product will be absorbed into the cytoplasm of the phagocyte, and that's how phagocytosis occurs. So now we're going to go off and talk about the specific immune response. Now this occurs whenever your lymphocytes and white blood cells. So lymphocyte white blood cells is your specific immune response. And it's triggered by the body recognizing foreign cells. We talked a little bit about foreign cells and transplants, blood transfusions. So there's self and non-self then. So a foreign or a non-self cell will not be recognized by the body. And so if it is detected, it will process the immune response. Molecules are often protein, as they're referred to as antigens. So antigens are pretty much proteins. Different pathogens will have different antigens, and an immune response will be specific to the antigens, as a lymphocyte will have a receptor that's complementary in shape to the antigen. So, for example, one disease will have a specific antigen, another one will have a different antigen, and etc., etc. And so these lymphocytes must have a complementary in shape receptor that binds onto each one of these. So it can be quite slow. So an antigen is then basically just chemicals that are capable of producing a specific immune response. So how can you tell the difference between self and non-self cells? Well, there's different types of lymphocytes to start with, each having receptors with a complementary shape to the antigen. In the fetus, lymphocytes are frequently making contact with other fetal cells, but the lymphocytes complementary in shape to the fetal are switched off. So when the fetus is born, functional lymphocytes are not complementary to self cells, and then they won't target self cells. So many functional lymphocytes remaining, only a few of each type, and this is why it's slow. So although there only is many functional lymphocytes remaining, there's only a few of each type to target each disease. So Types of lymphocyte then. You have B lymphocytes and T lymphocytes. B lymphocytes are formed into stem cells in the bone marrow, and they mature in the bone marrow also. The immune response is antibody-mediated, and their nature of the response is that they produce antibodies which respond to antigens in body fluids. They can be bacterial and viral. T lymphocytes, however, are also formed in the bone marrow, but they mature in the thymus gland, and their immune response is cell-mediated. The nature of their response is that they respond to antigens in body cells, and they're usually only viral. That's quite key. So, lymphocytes activation then. The specific immune response will require an antigen to come into contact with a complementary lymphocyte, and this takes time due to the small numbers involved. But when it happens, the lymphocyte will become sensitized. The B lymphocytes will have its genes activated to get in motion a process that leads to the production of antibodies. So basically, antibodies will be produced. So then T lymphocytes, a number of T cells will be produced, and in both B and T lymphocytes, they will both become sensitized, and lymphocytes are cloned by the division of mitosis. So cell-mediated immunity then. This is for your T lymphocytes. So in their immune response, production of T cells is referred to an antigen-presenting cell, and the macrophages will be engulfed and broken down a pathogen, or break down a pathogen. Any type of body cell that has been invaded by a virus presents an antigen on its cell surface membrane. So the foreign antigen is on the membrane. Cancer cells will present an abnormal antigen on the cell surface membrane, like I just said. So the types of cells then that will be produced. So basically, the receptor will bind on. It'll then clone into a number of different cells by the division of mitosis, and these are some of the cells that are produced. So you have killer T cells, which destroy infected cells by attaching to the antigens on the cell surface membrane, and then they produce the protein perforin, which punches holes in the cell surface membrane, destroying cells. Helper T cells are produced, which stimulate B cells to divide and produce plasma cells, producing antibodies which promote phagocytosis. Phagocytosis will be slow without activating helper T cells, as these attach opsins to the pathogens, marking them out for phagocytosis, and they also secrete interferon, helping limit the ability of the virus to replicate. Memory T cells will circulate in the body fluid and respond rapidly to future infection by the same pathogen. If a subsequent infection occurs, memory cells are sensitized rapidly, producing a large clone of T lymphocytes. And finally, you have suppressor T cells. These cells suppress the immune response of other cells when it's required. They're also important in preventing an autoimmune responses when the immune system attacks cells in the body. So basically, it stops the immune response when it doesn't need to go on anymore. So, antibody-mediated immunity. This targets bacteria or viruses found in body fluids and defends the body through the production and action of antibodies. An antibody is a globular protein which is complementary in shape to specific antigens and can react with antigens, leading to their destruction. Specific antigens will sensitize specific B lymphocytes, and receptors will match the pathogen's antigen. So B lymphocytes will become cloned, very similar to T lymphocytes, but they'll produce plasma and memory cells. The plasma cells are short-lived, but they produce a very large number of antibodies, and these antibodies will neutralize the pathogens as a consequence of antigen-antibody reactions. So the action of antibodies then. Antibodies produced as a consequence of a specific antibody-mediated response. The antibodies will latch onto the bacterial antigens, clumping the bacteria together. The buildup of antibodies causes agglutination or clumping as an antigen-antibody complex. This antigen-antibody complex is engulfed by polymorphs and other phagocytes, and the antibodies will also act as opsonins, which will attach to the pathogen, marking them out for phagocytosis so they know where to go. Memory cells will also be produced by B cells, and these will divide rapidly, producing a vast number of plasma cells. And these plasma cells will produce the antibodies to destroy the pathogen. The memory cells will guarantee long-term protection, known as the secondary immune response. The primary immune response is initial response to the antigen when it's meeting for the first time. Thank you, ladies and gentlemen, for watching this here. We are now finished the immunity, and we will be moving on to neurons. Thank you for watching. I've been Dylan from C.A.R Entertainment, and I'll see you next time.